Apoptosis, also called programmed cell death, is the process where the cell regulates its own death through the production of certain enzymes. These enzymes cause degradation of nuclear and cytoplasmic material, and the cell breaks into fragments called apoptotic bodies. These apoptotic bodies are then gobbled up by phagocytes. Apoptosis could be triggered by factors such as infection, especially viral infections, misfolding of proteins due to mutation, and DNA damage due to mutation, radiation, hypoxia, and free radicals. Now, apart from pathologic factors inducing programmed cell death, apoptosis is also a homeostatic mechanism where cells that are not needed are killed, thereby maintaining a steady-state population of cells. During apoptosis, the cell undergoes certain morphologic changes that can be seen in light and electron microscopy. The cell shrinks and becomes smaller in size, and the cytoplasm and organelles become tightly packed. The nucleochromatin shrinks and becomes condensed at the center or the periphery, a process called pycnosis. Following this, chromatin material undergoes karyorexis, that is, it disintegrates and becomes fragmented. Under the microscope, a cell undergoing apoptosis would appear shrunken, with a dense eosinophilic cytoplasm and small clumps of hematoxophilic chromatin material. Further, the cell starts to form blebs on its surface and starts to break off into small fragments called apoptotic bodies. These apoptotic bodies have portions of the cytoplasm, organelles, and also nuclear fragments of the cell. Now, it is important to understand that apoptosis does not elicit any inflammation, unlike another form of cell death called necrosis. This is because apoptotic bodies have an intact plasma membrane and prevent any content from leaking out to the interstitial space. Also, apoptotic bodies are quickly recognized by phagocytes and removed from the environment. A cell can undergo apoptosis due to several reasons, and depending on the etiologic factors may have three different pathways of initiating cell death. Apoptosis could be initiated by signals from the intrinsic pathway, the extrinsic pathway, and the perforin granzyme pathway. In the intrinsic pathway, mitochondria become leaky and ooze out proteins called cytochrome C, which initiate apoptosis. Usually the cytoplasm and mitochondrial membrane harbor proteins called BCL2 and BCLX, which are anti-apoptotic, and preserve the integrity of the mitochondrial membrane, preventing apoptotic proteins like cytochrome C from leaking into the cytoplasm. However, in the absence of a growth signal, or due to insults like radiation or protein misfolding, stress proteins called BH3 only proteins are stimulated. These BH3 only proteins, comprising of BIM, BID, and BAD proteins, block the function of BCL2 and BCLX. These proteins further activate two pro-apoptotic effectors called BAX and BAC, which create channels in the mitochondrial membrane, allowing intramitochondrial proteins like cytochrome C to leak into the cytoplasm. Cytochrome C in the cytoplasm binds with a protein called apoptosis activating factor 1 to form a complex called apoptosome. This complex binds with caspase 9 and begins to cleave and activate adjacent caspase 9 molecules. Caspase 9 is an initiator caspase, and activated caspase 9 molecules activate executioner caspases like 3 and 6, leading to apoptosis of the cell. Cytotoxic T lymphocytes, or CD8 T cells, cause apoptosis of infected cells or tumor cells by Fas ligand and Fas receptor interaction. Many cell types express a receptor called the Fas receptor, and cytotoxic T cells express Fas ligand. These cytotoxic T cells bind to the Fas receptor on tumor cells or infected cells through their Fas ligand. And this interaction may produce apoptotic signals through two pathways, the extrinsic or the granzyme perforin pathway. The extrinsic pathway involves binding of an adaptor protein called Fas-associated death domain to the cytoplasmic end of at least 3 to 4 Fas ligands. This then binds with caspase 8, another initiator caspase, which gets cleaved to become active. The active caspase 8 further activates other caspase 8 molecules. And these in turn activate executioner caspases 3 and 6, leading to apoptosis of the cell. At times, the granzyme perforant pathway is initiated on fast ligand fast receptor interaction. T cells release perforins which form transmembrane pores on the cells, through which granzymes and other proteins secreted by T cells enter. Granzymes could either directly activate executioner caspase molecules or cause DNA cleaving leading to apoptosis. Executioner caspases 3 and 6 cause degradation of chromosomal DNA and also degradation of cytoskeletal proteins, which cause morphological changes such as nuclear fragmentation and cellular shrinkage respectively. However, it is not yet known what causes changes like cellular blips and apoptotic bodies. Apoptotic bodies are coated with a phospholipid called phosphatidylserine, which is recognized by phagocyte receptors. Also, apoptotic bodies may be coated with opsonins like antibody IgG or complement proteins like C3b, which are recognized by phagocytes, thus facilitating rapid phagocytosis of apoptotic bodies.